In the world of AI, the mantra for years has been pretty simple. Bigger is better. More data, more computing power, more parameters. But what if that's not the whole story? We're about to dive into some really fascinating new research that completely flips that idea on its head.
So here's a weird paradox for you. These giant language models, they can compose a sonnet, they can write code, but if you give them a logic puzzle like Sudoku, they can just completely fall flat on their face. Think about it. One single wrong number and the entire solution is garbage. This fragility, when it comes to problems that need strict, step-by-step reasoning, is one of the biggest challenges in AI right now.
So why does that happen? Well, it's not really a failure so much as it is a feature of their design. See, these models generate answers one piece at a time, token by token. And that's incredible for creative tasks, but not so great for rigid logic, where one little mistake can cascade and ruin everything. Researchers have been working like crazy to try and patch this up.
One of the most common fixes you'll hear about is something called chain of thought. It's basically where you tell the AI to think step by step. And yeah, it helps, for sure. But it is no silver bullet. The technique can be really expensive. It needs a ton of high-quality examples to learn from, and honestly, it's still pretty brittle. The reasoning it spits out can be flawed, which just leads you right back to where you started.
Okay, so this brings us to a really clever but very complex attempt to solve this called the Hierarchical Reasoning Model, or HRM for short. The idea was, instead of trying to patch up a giant general-purpose model, why not build a specialized system from the ground up, designed just for this kind of hard reasoning? The only problem, it was incredibly complicated.
I mean, just look at all the moving parts this thing had. It was basically a Rube Goldberg machine. It had two different networks that were running at different speeds, and this was all based on these really complex arguments about how the human brain might work. And here's the kicker. To save on computer memory, it used a mathematical shortcut that, well, wasn't even guaranteed to work. An ingenious idea for sure, but maybe a little too intricate.
And hey, don't just take my word for it. This quote comes directly from the very researchers who would later challenge this whole approach. They saw the promise in HRM, but they also saw how fragile it was. The foundation was clever, but maybe just a little bit shaky. And that skepticism is exactly what sparked a major breakthrough. So here's the big idea. What if the solution wasn't to try and fix HRM's complexity, but to just get rid of it altogether? And this is where our hero model comes in, the Tiny Recursive Model, or TRM. Its creators took one look at that intricate machine and basically said, okay, what happens if we make this thing radically, almost shockingly simple? What you're seeing here is a complete philosophical shift. TRM didn't just tweak HRM, it threw out all the complex parts. So instead of two networks, it used just one. It ditched the complicated biological story for simple, intuitive logic. It got rid of that risky mathematical shortcut and just used a direct, straightforward learning process. And the size? The parameter count went from 27 million all the way down to just 7 million.
So, how on earth did simplifying everything lead to a better result? Well, it all came down to a few key changes that pretty much defied all the conventional wisdom in AI.
Okay, this right here is the heart of the breakthrough. Remember that shaky mathematical shortcut HRM was using? The researchers tested what would happen if they just got rid of it and did the full memory-intensive calculation instead. And the result? Wow. Accuracy on hard Sudoku puzzles jumped from about 56% to a staggering 87%. It turns out that shortcut wasn't just a shortcut, it was a roadblock.
And the rest of the formula was just as elegant. First, they figured out one network could easily do the job of two, which immediately cut the model's size in half. Second, they reframed the whole problem. It wasn't about some high-level and low-level thinking anymore. It was just a simple feedback loop of proposing an answer and then using reasoning to make it better. And then came the most counterintuitive step of them all. They found that a tiny network with just 2 layers was the sweet spot. A bigger network with 4 layers actually performed worse. Why? Because it started to overfit. It basically just memorized the training examples instead of learning the actual logic. So in this case, being smaller actually made the model more robust and way better at generalizing. Less was truly more.
Okay, so the theory is elegant, right? The simplifications are really smart. But did it actually work? This is where the story gets really, really good. Let's look at the results.
First, let's just get the scale of this in our heads again. TRM is about a quarter of the size of the already small HRM. And just to give you some perspective, a bar representing a major LLM like Gemini, it wouldn't even fit on this slide. It would be miles high.
So how does our little 7 million parameter model actually do? Well, on the super hard Sudoku Extreme dataset, it absolutely crushes its more complex predecessor. It goes from 55% accuracy all the way up to 87%. That's just a massive leap in performance from a model that's 4 times smaller.
And this wasn't just a one-trick pony. They also tested it on the ARC-AGI benchmark. Now, this thing is a notoriously difficult set of abstract reasoning puzzles. They're designed to be easy for us humans, but really hard for AI. And what do you know? TRM comes out on top again, beating HRMM. But this is the knockout punch. TRM, with its tiny 7 million parameters, doesn't just beat HRM, it beats Google's Gemini 2.5 Pro, a model that has over 32 times billion parameters. Our tiny model, with less than 0.01% of the parameters, got a higher accuracy score on this specific, difficult reasoning task. I mean, that is an absolutely stunning result. So, what's the big takeaway here? This is about so much more than just solving a few puzzles. This result really points toward a potentially new and, frankly, very exciting direction for the entire field of AI research. For years, the path forward just seemed to be building bigger and bigger models. But this suggests there's another way. A future where we focus more on clever, efficient algorithms instead of just throwing more raw computing power at the problem. A future with smaller, more specialized, and more accessible AI models that can solve hard problems without needing a planet-sized dataset or a supercomputer to run them. And that leaves us with one last provocative question to think about. This tiny little model has shown us that on certain really crucial tasks, smart design can actually beat brute force. It challenges the very foundation of the scaling laws that have governed AI for the last decade. So, is the future of AI really about getting bigger, or is it about getting smarter?